We will continue with the talk on planetary nebula shaping agents with Garcia Segura giving us a talk on single rotating stars and the formation of bipolar planetary nebulae.
Thank you. Single star. Thank you, everybody. This morning is the last one. We're tired. I'm going to be short. This work has been done in collaboration with Eva Villaver, Norbert Langer, Sun Jun, and Arturo Machado. We are going directly to the point because this is an audience that is an expert in the field, so no introduction and no, just to the punchline. This is going to be a negative result, but I think in this context it's going to be positive. So I'm going to show you the first computation of a 2.5 solar mass model all the way from the main sequence to the post-AGB with a rotation of 250 km per second initially, and I'm going to show models that include magnetic torques or not, both. This is stellar evolution code actually from the Norwest group. We have to say gamma ray bars and pulsars because these codes were made for this kind of business. So nobody cares about planetary nebulae, stellar evolution. So, anyway, I'm going to compute these masses with the Basilea-Istanbul mass loss rate. So we start here in the main sequence. We go to the regional branch. We go to the AGB. In the thermal pulses, we lose a lot of mass, especially in the last two thermal pulses. We lose so much mass that the Hayashi track shifts to the left, to the right, sorry. And then we go back to the post-AGB. So it's nothing new in the chart diagram. We are not going to talk about chemistry or whatever. We are going to focus on the rotation at the surface. So here we go. This is a model with no magnetic field inside the star, and this is a model with magnetic braking. What happens here in the surface of the star? We start initially at 250 kilometers. This is, by the way, kilometer per second, the surface velocity, and this is time. This is time here and then there. So we are in the main sequence. We have in the main sequence the core contract. Then we go to the regional branch, then to the helium burning phase, and then to the late AGB, and this is the thermal pulsing AGB. We can see that at the thermal pulse, of course, the star expands and contracts and so on, and you see the modulation in the rotational velocity. At the end, in the last two thermal pulses, we lose so much angular momentum because of mass loss that the star completely slows down. And slow down, I mean that the surface at the post-AGB when you 6,000 Kelvin is less than a centimeter per second. In both cases are exactly the same, less than a centimeter per second. And in the last, just previous to the last thermal pulse, the AGB, which is the biggest radar at that time, only have around 300 centimeters per second. So basically zero. This is what you see at the surface. So what is the difference between magnetic braking or non-magnetic braking? Why we should include magnetic braking? At the surface the same. Well, this is why gamma ray bars and pulsars came into this business. If you see now the structure of the star, this is radius, this is inside of the star in centimeters, logarithmic scale, and it's going to be in kilometers per second the rotational velocity. So what's happened here, start at the 0H main sequence with a solid body rotation, and then when this is 0H main sequence, end of main sequence, this is the contracted helium core, then we go to region branch, the core has contracted much more, then helium main sequence expands a little bit, at the post-AGB, which is also the late AGB, the core is rotating really fast, 150 kilometers per second. This means that you see here 10 to the 9 centimeter. This is the white dwarf. Basically, the white dwarf is going to rotate at 150 kilometers per second. Now, with magnetic braking, the scene is completely different. We start with the same conditions. We end up at the mid sequence a little bit different because we are transporting all the angular momentum from the core to the envelope. Once that the star expands to the radial drum, here the radius is 25 solar radii only, you have slowed down completely the core. The radii is rotating at 5 kilometers per second, but the core is already slowed down. And when you go to the post AGB, at 6,000 Kelvin, this is the white dwarf that you are going to get. A white dwarf basically 4 or 5 kilometers per second rotation. But we know from observations that white dwarfs do not rotate faster than 10 kilometers per second, usually. Normally they are slow rotators. So, you need to include magnetic braking to solve the problem of a slow rotation in white dwarfs. So basically, this is the kind of model you have to push. Because white dwarfs is a very important observable. Alright, back in 1999, we didn't have these tools, of course. We were doing analytical approximation, some trying of guessing what was going to happen in this scenario. So at that time, we proposed two scenarios. One was the pessimistic one, which post-main sequence star about 1.6, suffer magnetic braking, and then their helium cores are spun down. This is what we found with the magnetic braking models. So this should be the one that we had to take, the pessimistic one at the time. At the optimistic scenario, the helium core evolved decoupled from the envelope, as we saw in the one with non-magnetic braking, retains angular momentum, but we said at that time that for some mechanism, the core envelope angular momentum has to be exchanged. Otherwise the white dwarf rotates very fast. As we saw in the non-magnetic braking model, this is the specific angular momentum at the surface. We really transport a while the angular momentum to the surface in some places, for example here at the thermal pulse, just a little bit. But at the end, the mass loss is so huge that it doesn't matter what you do. At the end, you lose all the angular momentum because of mass loss. It doesn't matter internal structure anymore. Just to be sure that we want to get back to that optimistic case, we are going to do 3 experiments, 3 academical problems with no sense, physical sense, just artificial, just to check this. So what we did was we ran 3 models with no magnetic braking up to 3 points in the evolution where we are going to switch the magnetic field at the end, just to try to put all the angular momentum of the core to the envelope at the end to see what's happening, which is the most favorable case. So these points were selected at the beginning of the thermal pulse IGB. This is helium luminosity versus mass. So here you see the thermal pulses. You see that in the two last thermal pulses, you lose most of the mass, more than a half of the star. So point A, we switch the magnetic field here. In the model B, we switch the magnetic field here, and in point C, we switch the magnetic field. 3 different experiments. So what it comes out from that is that in model A, which is at the beginning of last thermal pulses, I'm showing you again the rotational curve. This is the internal structure of the star. These are kilometers per second, the rotational curve. So in model A already the post-AGB, We have also a Y2R 10 to the 9 centimeter, slowly rotating at 5-6 kilometers per second. And the structure of the envelope, the convecting envelope, practically the same, zero velocity. For the case B, before the two last thermal pulses, you end up with 15 kilometers per second with the Y2R. But again, in the surface, you don't do practically anything. And in the model C, which is it should be the most favorable one, you don't get too much thing also at the surface, only at 2 kilometers per second. But this model already has passed all the superweak phase, so there is no way that you can get an excretion disk or whatever, and it has the equator in the flow. Okay, perfect. So now we have very precise number, and we can play with those numbers. For example, we start with the angular momentum, the total angular momentum of the star. At the beginning of in the 0H main sequence, we have an angular momentum of 10 to the 50 in CES units. When the AGV is 1 solar mass and radius of 466 solar radius, the angular momentum that you get for the whole star is 5 times 10 to the 48. This is a factor of 125. And you lose that angular momentum because of the mass loss, which is a lot. Now, this is the funny part. You can split the AGV in core and envelope. If you compute the angular momentum of the core for the non-magnetic braking model, it's 4 times 10 to the 48. And the envelope is just 10 to the 48. So it is true the angular momentum is kept in the core. So now, we know that at least we need 2 kilometers per second at the surface of the AGV if you want to do some asymmetrical in the flow with asymmetries, like the Harman-Casinelli body or something like that. So with 2 kilometers, we will be dreaming. So if the star in this point is rotating at 300 centimeters per second, we need to increase by a factor of 300 larger this value, which is translated in multiply the envelope angular momentum by this factor, which is 10 to the 51, right? But look at this number, 10 to the 51. The 0 sequence, 10 to the 50. So it is larger than the initial one. It's impossible for a single star. You can lose angular momentum, but you cannot gain angular momentum. So this is the key. Single star cannot rotate at the AGV so fast. It's impossible. But this is nothing in angular momentum in the cosmological context. This is exactly what 6 Jupiter masses at 5 astronomical units is going to get you. So you just can spin up easily an envelope with planet, brown dwarf, or your favorite animal. So conclusions, it is really hard to get single star rotating at the late AGV and post-AGV to form any kind of asymmetries and bipolarities. And the second point, well, of course, with the actual tools, what we have is a state-of-the-art calculation. And the second point is that you really need external angular momentum from another planet, brown dwarf, or whatever to spin up the AGVs, especially the AGV envelope. As Noam Soccer always says. Thank you.
We have about 1 minute for a question or two, or a comment. I have one, which is that there are 2 wonderful constraints. If you can quickly back up, Guillermo, to your initial surface rotational velocity plot on the thermally pulsing AGV. Right there. So we just heard yesterday about TX cam, which is rotating, and I forget the number, 1.7 kilometers per second if the modeling of the maser spots holds up. So that would put it, assuming the star's in the thermally pulsing AGV, One very interesting constraint, and the other interesting constraint is that the massive planet around Beta Pic that I mentioned yesterday, which is some estimates between 5 and 10 Jupiter masses, I believe, at 10 AU. So perhaps this is enough to get. Questions? Other questions? Oh. Very quickly.
There is a paper a few months ago by Van Bell et al. Who measured the ellipticity of HB stars.
The what, sir?
The ellipticity of HB stars, and they derive rotational velocity from between 5 and 10 kilometers per second E sine I. And those are not decent mass stars, so it seems to be a bit higher in your finding.
Wait, I mean, stars, any star rotates, and they can rotate faster, even at 13 kilometers per second. The key is that you cannot get the rotation by a single star. You always need help. I mean, it's fine, they can rotate, but they need help.
I'm sorry, we don't have time right now. We have to wait till the discussion part of the session. I have to be very brutal because I have a plane to catch. I have to be out of here at 12:45. So I'd like to ask the next speaker to Wolfgang Stefan, who will tell us about multipolar planets.